broadcast, everybody gets it. If there's a collision, well, somebody might get it a nanosecond later, but they all eventually figure that out. Here, it's entirely possible that A is sending messages to B, and C is no problem because there's no interference. At the same time, C is sending messages to B, and C is seeing no interference because they don't reach each other, and B is not hearing a thing because it's getting messages at the same time from two that are interfering, and none of the senders know about it. So, and exactly the same issue here with the hidden terminal. Okay. Any questions? Okay, we'll go a little bit further. And for some reason, one overhead got strangely deleted here. So, talk about is CDMA, which stands for Code Division Multiple Access. Okay. So, have you heard the term CDMA? No? Never? Where did you hear of CDMA? Cell phones? Don't they advertise CDMA sometimes? So, you already know about TDMA and FDMA, right? Time division multiple access and frequency division multiple access that we saw. So, what all this is about is sharing, and this CDMA is commonly used for wireless sharing, including cell phone networks. So, time division, we knew that you have various time slots, and different users use different time slots, so on. So, you get one slot, then you wait 3 slots, and then you get the 4th slot. FDMA is you break up your medium into frequencies. You have F1, F2, F3, F4, and everybody gets a share of the bandwidth based on the frequency that they are told to operate on. So, here is code division multiplexing. So, the interesting thing here is that a bunch of nodes simultaneously broadcast on all frequencies and all time zones. Okay, so they don't make any specific rules saying this time is yours and this time is mine. They're all using broadcasting all the time, but they have different codes. Okay, so the basic idea is that actually let's get back. The basic idea. Sorry. Is that you have user 1, let's say A, B, C, D, and they each have their own code. Okay, code A, code B, code C, and code D. Okay, so everybody sends their message, and that gets coded. Okay, so a new message comes out, coded message, so it's a little different. Okay, and all of this goes on the same wire. So you just let them mix it up. And let's say A was talking to X and B was talking to Y. Okay, so over here you have X and you have Y, and the coded message comes in, and let's see, you can decode with A's code, right? So X knows A's code, and even though all the messages were jumbled up, and X gets not just A's message, but this whole stream that includes A's, B's, C's, and D's messages. But so long as X knows the code with which A's message was coded, it can extract A's message from the mixed signal. Okay, so that's the basic idea. You let everything mix. You don't partition anything, but if you follow some rules, everybody can get the specific message that somebody sent. Okay, That the basic idea is clear? So, but how can you do that? Okay. So we're not going to completely understand the entire mathematics of why or how this works. But here is a basic idea that one sender, we're talking about only one sender in this case. Okay. So one sender is given a code. So the code in this case is the code consists of ones and zeros, except that instead of 0, you call it -1 here. Okay. So the code here is 1 1 1 -1 1 -1 -1 -1. So the code has 8 components, basically zeros and 1, except we call 0 -1. So when this sender wants to send a 1, this is real data. Instead of 1, it encodes it by multiplying every bit with the code, and it gets, in this case, it gets this output. Okay. And this is essentially exactly the same as the code. The code was 1 1 1 -1 1 -1 -1. The output when you're sending a 0 is exactly the same. It is 1 1 1, this thing. And when you're sending a 0, this is the second bit, you get this. Okay. What's the relation of this one to the code? This byte here, or that's basically. Is it the same as the code? It's obviously a mirror image, right? So you multiply the code by -1, and you got the mirror image. So every time there's a 1, there's a -1 here, and so on. Okay, so that's pretty easy. Zeros, you send the whole code. Ones, you send the opposite of the code. You negate everything. If it is wherever it was 1, you make -1. Wherever it was -1, you make 1. Okay. So then this stuff shows up at the receiver. Okay. And the receiver basically looks at it and applies this to decode. The receiver also has the code. So zim.cm is basically multiplying each, multiplying, if this thing comes in, multiply each bit with the code and add it up. So the code was 1 1 1 -1 and so on. So it is 1 1 1 -1 1 -1 -1 -1. And you're essentially multiplying it by itself because one was sent. I'm sorry. I may have confused 1 and 0 here, but anyway, one of the values is sent as code, the other is sent as the reverse of the code. I confused these two. This was actually sending a 1. It was data 0, called it a 0. Okay. So 1 was sent. It is exactly the same as the code, and you multiply it by the code and add it pairwise. Okay. So this one multiplied by 1 is 1. Second again is 1. This is again 1. -1 multiplied by -1 is again 1, right? So you're going to get here, this will be 8, and you divide by m, the number of bits. So you get 8 by 8 equals 1. Okay. So you pairwise multiply each of those things with the code and divide it by number of components of the code, and you'll get 1 or a 0. Okay. Any questions? That makes sense? It's quite. So you were sending a 1. It became 1 1 1 -1 -1. I'm making lots of mistakes. One more time. You were sending a 1. It became 1. Became 1 1 1 -1 1 -1 -1 -1. Then it reached the other side. This was the code itself. You multiplied it by the same thing, and then you added everything pairwise multiplications. You get 1